We want to start off Chapter 7 by going back to the idea of the types of bonding and kind of expanding out what our definitions that we established in the beginning of the class. So this is actually a bit of review, right? We talked at the beginning of the semester about the fact that we have ionic bonds and covalent bonds. Ionic bonds, chemical bonds between ions. There's that transfer of electrons between atoms. Covalent bonds between neutral atoms, and we have sharing of electrons. So that was just kind of what we said at the beginning, kind of just said that defined what was going on. Now that we have a bit more of an understanding of what electrons are doing around atoms, we can start to understand and explain a bit more of the actual mechanism that's going on here. So when we have ionic compounds, it requires an anion and a cation, right? We know there has to be a negative and positive charge. And we've said anions were our nonmetals, and then cations were our metals. So we use that to characterize, if something is a metal or has a metal in it, that means it's an anion. Cation, which means we have an ionic compound, right? There's an anion and a cation. We use that to characterize what type of bonding was going on in each a given compound. Now we have a little more understanding that we know there's this transfer of electrons, that the metal atom is going to lose an electron to become a cation, and that the non-metal is going to gain that electron to become the anion, right? So we have the cation and anion, now positive, negative charges that are attracted to each other. And the reason why metals tend to form cations is because metals have a relatively low ionization energy. We know that elements on the left side of the periodic table have lower ionization energies, and it's easier to remove an electron. At the same time, nonmetals on the right side of the periodic table have high electron affinities. That means there's a lot of energetic gain to becoming an anion. So something like chlorine as an atom, there's a lot of energy to gain by becoming an anion. A metal like sodium has a low ionization energy. It's not hard to remove that electron. And so the sodium can lose that electron, low cost, and then chlorine, when it gains the electron, has a big gain. So that's why our metals always become cations and our nonmetals become anions. We can understand it based off the underlying periodic trends of what's going on with those electrons. A nonmetal does not form cations because they tend to have high ionization energies. There's a really big cost to doing it. And conversely, metals don't become anions because they have low electron affinity. So there's not a lot of gain for them to become an anion, so they can't take an electron off of something else. So there's low bang, so there's low gain to it. You don't get a lot of energy out of it, so there's not really much drive to take an electron from another atom. So when we have that transfer, you end up with an electron from something that has a low ionization energy, something with a high electron affinity, or metal to nonmetal. You get that cation anion, and then that positive negative charge holds those ions close together in what we call an ionic bond. So then covalent bonds, we know, are when we have this shared pair of electrons. And covalent bonds form between atoms with high electron affinities. So high electron affinities correspond to elements or atoms that want to gain more electrons, right? They want more electrons around them. And so this is going to be when you have two atoms that do not want to lose electrons. So for example, two nonmetals. And so nonmetals are what are always going to participate in covalent bonds because they have high electron affinities. They really want to all gain more electrons, and covalent bonding offers that possibility. So when we form, we have this kind of idea of sharing electrons in a covalent bond, transfer of electrons in ionic bonds. The thing is, that depiction is a little kind of this idea of just two sides, or is a little not true. When you actually have atoms that are sharing electrons in a covalent bond, that sharing is not necessarily equal. And what's going on can be explained by a property called electronegativity. So electronegativity is a description of how much an atom pulls electrons towards it in a covalent bond. So for example, I have hydrogen and chlorine. Okay, so they can form a covalent bond where they're sharing two pairs of electrons, but they don't share those electrons equally. Chlorine has a higher electronegativity. We can see its value is 3, hydrogen's is 2.1. So chlorine's is larger, As a result, it pulls those electrons more towards it. Electronegative, it attracts the negative charge of the electrons towards it. Electronegativity is a periodic trend. It increases across periods and it increases up groups. What that leads to is the fact that fluorine is the highest electronegativity of all elements. We don't talk about the noble gases because they don't tend to form molecules, so we just truncated that fluorine. That has the highest electronegativity. When we have these electronegativities, this is a description of how strongly electrons are pulled towards the atom. So if I have a bond that is two atoms with equal electronegativities, i.e. they're pulling electrons towards themselves with the same force, that will mean that they actually equally share those electrons. And we call that kind of bond non-polar. There's no poles, there's no sides of the bond. The electrons are equally shared. If you have atoms with different electronegativities, then you will have unequal sharing of those electrons because they're just different electronegativities. That will lead to what's called a polar bond. When I say polar, that's so much like the north and south pole because there's two different ends of the molecule, the bond. One will be positive and one will be negative. So functionally, what we are going to care about are whether or not a bond is polar or nonpolar, and it's going to be based on having equal or unequal electronegativities. And for our purposes, that's going to be based on whether or not the atom is the same. So you'll note in this top, these are both chlorine. Since they are both chlorine atoms, they have to have the exact same electronegativity, and that's how we're going to generate nonpolar. If we have two atoms that are different types of atoms, then they're going to be nonpolar. There are some fringe cases. If you really try, you can find two atoms with very similar electronegativities. We're not going to worry about those fringe cases. We're just going to look at, are they different atoms? That makes them polar. Are they the same atom? That makes the bond nonpolar. So if we take a look at these polar bonds, we got this hydrogen and chlorine example. Those are different atoms. They're going to unequally share electrons. We know that the chlorine is more electronegative. What that means, there are more electrons on the chlorine side of the bond. It is pulling that shared pair more towards the chlorine. The electrons literally spend more time. They have more distribution on the chlorine end of the bond. So we put these lowercase deltas with charges. The little squiggly line is a lowercase delta, which is Greek letter D, so it means like difference. And so you can see that the chlorine has a negative delta. That means that the chlorine end of the bond is slightly negative, and the hydrogen end of the bond is necessarily slightly positive. When you have a polar bond, one end has to be positive and one end has to be negative. The more electronegative atom gets negative. That's where literally the word comes from. And so you'll note we're using these slightlys for the deltas because this is not ionic. This is not a full transfer of an electron. These electrons are still shared, they're just not equally shared. Chlorine's kind of a hog, it's pulling those electrons towards it. We can also see that there's a bond, or an arrow that's drawn above the bond. This is called a dipole moment. This arrow always points from positive to negative, and you'll even see that we write this positive across it, right? So that cross, that line that goes across the arrow is part of the dipole moment arrow. We literally draw a positive sign on the end of the arrow that's on positive, and we draw the arrow towards the negative end of the bond. Okay, so for each of the following bonds, I would like you to determine if the bond is polar or nonpolar, and if the bond is polar, determine the direction of the dipole moment. So let's walk through some examples here, see if we can figure out bond polarity. I got HF, FF, CO, and NN. So if I wanted to determine bond polarity, the first question to figure out whether or not a bond is polar is, do the atoms have different electronegativities? Because are they pulling with the same strength or are they pulling differently? Which is going to mean if they have different electronegativities, if they don't have different electronegativities, then it's definitely nonpolar because they're pulling equally. If it's a yes, then it's polar. That's what we're looking for. And really, that's just going to come down to, are the atoms different or the same? And then if it is polar, if we want to figure out which side is negative, we're looking for what atom has a higher electronegativity. Electronegativity is a periodic trend, so we're just looking for what atom is closer to F on the periodic table. Okay, so let's take a look at actually doing these. HF is the first one. Because those are different atoms, this has to be a polar bond. When we're looking at finding different or the same electronegativities, we're looking for, is it the same atom or are they different? So this is definitely polar. If we want to figure out the charges then, it's a matter of looking for which one is more electronegative. Whenever we see fluorine, that is the most electronegative element. Doesn't matter what it is, what molecule is in that fluorine, if it's a polar bond, is going to be slightly negative, and therefore the other atom has to be slightly positive. So one side is slightly negative, one side is slightly positive. So speaking of fluorine, our second example is F bonded to F. We want to see, is this polar or not? We have a tendency when we see fluorine just to jump to polar, but because they're both fluorine atoms, this is nonpolar. Both of those atoms are pulling electrons towards themselves very, very strongly, but they're equal, right? They're both really strongly pulling, so it's going to be a nonpolar bond. Carbon and oxygen now. This is, again, a different atoms. Carbon and oxygen are not the same atom. That's going to be polar. So we want to figure out now which side is going to be more electronegative. In order to do that, we can use the periodic table. And we can use the periodic table and ask, well, which atom is closer to fluorine? We can see that oxygen is 1 block away from fluorine, whereas carbon is 1, 2, 3 blocks away from fluorine. So oxygen is closer to fluorine on the periodic table. That means it's more electronegative. So oxygen gets the negative side and carbon gets the positive side. N to N, those are the same atoms. That's going to be a nonpolar bond. So this idea of bond polarity, when we're looking at these covalent bonds where there's unequal sharing of electrons, paints this idea that our kind of initial description of this dichotomy between covalent on one end and ionic on one end aren't just two modes of bonding, they are two extremes on a continuum of bonding. So if you have two atoms and they're forming a bond, if they have the exact same electronegativity, that would be pure sharing of electrons. If they have close electronegativities, but not quite the same, they're still going to share those electrons, but they share them unequally. Eventually, once you get to high differences in electronegativity, that's where you start to see ionic bonds, right? Electronegativity is truly a periodic trend. We only looked at it for, say, the nonmetals, but you can define it for metals as well. And because they're really far away from fluorine, they have really low electronegativities. So instead of unequally sharing, when you have an ionic bond where it features a metal, you just have a positive charge and a negative charge. The non-metal has such a higher electronegativity, instead of unequally sharing, it just takes. But when you have two nonmetals, they both still have relatively high electronegativities. They can share those electrons just unequally. And there's going to be a continuum. There's going to be very polar bonds and barely polar bonds. We're not going to worry about those particular numbers. We just want to know that this kind of complication really exists where our bonds are now polar when we're looking at these covalent bonds. So, that kind of distribution of electrons, where do they go? When we have the exact same atom, there's a small difference. There's no difference, right? Chlorine and chlorine. They're both very electronegative. They're both pulling those electrons very hard toward them, but they're canceling each other out. The electrons are actually equally shared. When you then go to polar covalent, we start to have some difference in electronegativity. Chlorine is a bit higher than hydrogen. You get sharing. Those electrons are spending time around both atoms still. That's what sharing means, right? It's kind of the orbital around the entire or both set of atoms, but it's kind of distributed more towards the chlorine. And then finally, in an ionic bond, this metal has such a low electronegativity that it just can't even hold on to that electron at all. It instead is a full transfer of an electron where the sodium becomes full plus, not slightly plus, right? There's no delta there, and the chlorine goes fully negative. Whenever we have a covalent bond, we want to keep those deltas. That's slightly negative, slightly positive. It's not the electron hasn't fully moved to the chlorine. It's just kind of a little shifted towards the chlorine side of the bond.